Distributed systems don't fail cleanly. They fail in weird, unpredictable ways. Welcome to The Explainer. Today we're diving into the chaotic but honestly fascinating world of large-scale internet applications. We're going to completely shatter that illusion of mathematically perfect computers and look at the messy, physical reality of what actually happens when you connect multiple machines together.
We have absolutely all been there, right? You're trying to buy concert tickets, you click purchase, and the loading spinner just hangs. So what do? Do you click it again? If you do, are you going to get charged twice? Or how about when you send a super important work message, it just vanishes, and then out of nowhere your boss gets 3 identical texts? Look, these aren't just random annoying bugs. They are symptoms of the underlying reality of distributed systems. Once your system spans across multiple machines, everything gets harder, especially communication.
So, here's how we're breaking this down. First, we'll look at the distributed system illusion. Then, we'll dive into unreliable networks and packets, the danger of partial failures, why time is an illusion, and finally, how to actually design for these messy realities. Part 1. The distributed system illusion. You know, we all kind of buy into this comfortable lie about computers, that they do exactly what we tell them to do. It's deterministic. But the absolute second you connect multiple computers over a network, that mathematical perfection completely evaporates.
Think about just a single laptop for a second. If there's a hardware fault, like, say, some bad memory, it usually just crashes completely, right? It fails fast. You get that dreaded blue screen of death or a kernel panic. And sure, it's highly annoying, but it is a clean failure. You know exactly what happened. The machine is dead. But in a distributed system, failure is fundamentally different. One machine might fail, while another completely healthy machine just keeps humming along, all while the network connecting them might be silently dropping messages in the background. We call this a partial failure, and because they fail silently and unpredictably, they are incredibly dangerous.
Engineer Kodahali honestly hit the nail on the head here. He said, "I've dealt with switch failures, accidental power cycles, and a hypoglycemic driver smashing his Ford pickup truck into a DC's HVAC system. I mean, wow. When you're building a distributed system, you aren't just writing elegant lines of code in a vacuum. You are literally at war with the physical world. You're dealing with real-world infrastructure, massive data centers, power grids, and just entirely unpredictable human errors. The physical world is violent, it's chaotic, it's absurd, and your software just has to survive it."
Moving to Part 2, unreliable networks and packets. And the primary battlefield of that chaotic physical world we just talked about? It's the network itself. In a shared nothing distributed system, the only way these separate machines can coordinate is by sending messages over an asynchronous packet network.
So, we need to talk about network partitions, sometimes called a net split. This happens when one part of your network is just completely cut off from the rest, due to some kind of fault. And here is the hard truth we all just have to accept. It is completely inevitable. No matter how much incredibly expensive, redundant networking gear you buy, you cannot entirely avoid network partitions. A human operator might just accidentally misconfigure a core router, or a construction crew might sever a critical fiber line miles away. Bottom line, faults are going to happen.
And when you send data packets over these physical networks, chaotic things happen. Packets can just be dropped entirely into the void, they can be massively delayed, they can even be duplicated by the network itself, arriving at their destination twice. And the causes of this packet loss? They are wild. It could be a disconnected cable, a bad software upgrade on a switch, or, and get this is a real thing that actually happens to undersea fiber optic internet cables. Sharks literally biting the physical lines at the bottom of the ocean. No way, right? But it actually happens.
Beyond just dropping packets, we have to talk about latency. Now, latency isn't just about a network being a little slow. The real issue here is that in an asynchronous network, delays are unbounded and totally unpredictable. This is mostly because of queuing. If multiple machines send traffic to the exact same switch at once, that switch's queue fills up. Your packet just has to sit there and wait its turn. Or if a virtual machine receives a packet, the hypervisor might just arbitrarily pause that VM for tens of milliseconds while another customer uses the physical CPU. We call that the noisy neighbor problem, and it makes network delays wildly variable. Ultimately, the network can drop, delay, or duplicate messages, and the terrifying part is you usually can't tell which one just happened.
Which brings us to Part 3, the danger of partial failures. When we combine these wildly unreliable networks with machines that might be actively crashing, we enter the really dangerous territory of partial failures.
Let's imagine how a double charge actually happens in the real world. Say Node A sends a payment request to Node B. Node A waits, but Crickets. Here's absolutely nothing back. Assuming the request was lost somewhere in that chaotic network, Node A tries again, sending a retry. But here is the nightmare scenario. Node B actually did receive the first request and process the payment perfectly, but its reply, that got delayed or dropped by the network. Now, because of that completely innocent retry, Node B receives the request again and processes the payment a second time. Your customer is furious, and your system just failed.
Put yourself in the shoes of that server node for a second. You send a critical message, and you hear absolutely nothing back. Your internal timer just runs out. Well, did your request fail, or is it just delayed? Is the other machine completely dead, or is the network just congested? The terrifying truth of an asynchronous network is that there is literally no way to know. You cannot distinguish between a crashed node, a dropped request, or a delayed response. All you know for sure is that you haven't heard back yet.
Part 4. Why time is an illusion. You might be thinking, okay, if we can't trust the network and we can't trust the other nodes, surely we can just rely on timestamps to figure out what happened when, right? Unfortunately, in a distributed system, even time is an illusion.
Here's the deal. Every single server has its own hardware quartz clock, and those clocks physically drift. They actually run faster or slower based on the physical temperature inside the data center. It's crazy. We try to synchronize them over the internet using the Network Time Protocol, or NTP, but network delays make NTP inherently inaccurate. Then you have leap seconds, an extra second added to the clock to account for the Earth's rotation. A single leap second famously crashed half the internet back in 2012 because systems just weren't prepared for the time to suddenly jump. And if you're using virtual machines, the hypervisor can pause your VM, making your application's clock suddenly leap forward without any warning whatsoever.
Because of all this, there is no single global source of truth in real time. Knowledge is entirely local. You can't rely on timestamps to perfectly order events because the clocks themselves are basically just guessing. Every single machine in your cluster is sitting in its own little bubble, making decisions based on incomplete, localized information, delivered over a network that might be straight up lying to it. Two different machines might completely disagree on when a specific transaction actually happened.
All right, Part 5, Designing for Messy Realities. Now, I know this all sounds like some kind of existential tech nightmare, but don't despair. Let's talk about how software engineers actually build highly reliable, scalable applications despite all this chaos.
Good distributed systems assume failure and design around it, not against it. We don't try to mathematically prevent the network from failing. We build software that survives when it inevitably does fail. One key way we do this is through quorums. Because no single node can be fully trusted, we rely on a majority vote. If one node thinks it's 2 p.m. and a transaction failed, but 3 other nodes think it's 2:01 and the transaction succeeded, well, the majority simply outvotes the weird node. We also build heavy observability into our systems, constantly monitoring for these silent partial failures so we can react dynamically before the customer even notices something is wrong.
And to solve that terrifying double charge nightmare we discussed earlier, engineers use a concept called idempotency. It sounds fancy, but it simply means designing an operation so that if you accidentally execute it multiple times, the end result is exactly the same as if you ran it just once. You might do this by attaching a uniquely generated ID to the initial payment request. If the receiving server sees a retry with an ID it has already processed, it simply replies "already done" without actually charging the credit card again. This is exactly how we safely navigate the ambiguity of retries and network drops.
Understanding these physical limitations is the absolute first step to building reliable data-intensive applications. These aren't just edge cases, folks. These are everyday realities at scale. You can't fight the physical world. You have to engineer for it. Distributed systems are fundamentally, inevitably uncertain. So I'll leave you with this thought. Right now, somewhere in your tech stack, a component is failing, a packet is dropping, or a clock is drifting. Your system is already failing. So, how are you going to design around it? Thanks for joining me on this explainer, and keep building resilient systems.